Okay.
The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. Welcome to the CPM Century Extrusion webinar for October 2017. Today's topic is Understanding Screw Element Metallurgy. My name is Letha Polk, and I will be your moderator for today's webinar. Century Extrusion is located in Traverse City, Michigan, USA, and is a global leader in the supply of twin screw extruders, extrusion systems, replacement parts, and support services for industries including compounding, master batch, powder coatings, human food, and pet food. Century delivers value with its line of twin screw extruders and extrusion systems by focusing on total cost of ownership, maximum reliability, and fast aftermarket service. Century also offers the industry's most comprehensive selection of twin screw replacement parts that includes specialty wear and corrosion solutions. Century will help you maximize your productivity through a wide offering of services, including consulting, screw design optimization, metallurgical analysis, twin screw training, and a range of implant services. Today's presenter is Mr. Bob Stratz. Bob is the head of engineering at Century Extrusion and has been with Century for more than 20 years. He has been in the extrusion industry for more than 30 years, working at various OEMs. If you have any questions during the webinar, please put them in the questions field. We will now turn it over to your presenter, Bob.
Thank you, and welcome to Century's Understanding Screw Metallurgy webinar. Currently, we manufacture screw elements ranging from 10 millimeters to 410 millimeters in diameter. They may be single key, multiple key, hex, or spline driven. We provide not only standard screw elements, but many custom profiles as well. And that would be driven by our customers and/or our process engineer, Adam. We pride ourselves on providing the best cost per wear and corrosion resistance available today. Our ability and willingness to match high-performance alloys, steels to specific applications sets us apart from many others in the industry. Currently, we offer over 80 metallurgical solutions, many of which were driven for a specific problem. The outline today is we'll be discussing the common materials of construction and the advantages and disadvantages associated with them, the composition of various materials and how alloying elements affect abrasive and corrosive wear resistance. Finally, we will be discussing the manufacture and testing of various materials, how they are produced and how they're tested for wear and corrosion resistance. Common materials of construction: nitrided, including nitraloy and many other steels containing aluminum as an alloy. Solid tool steel such as D2, powder metal 10V, etc. The martensitic stainless steels like 440C, 1.4122 and more. The austenitic stainlesses such as the 304 stainless, 316 stainless, and other austenitic stainlesses. The super alloys, that includes the Inconels and Hastelloys. The austenitics and pH steels and super alloys are most often hard face welded on the crest to offer an extra degree of abrasive wear protection while also providing excellent corrosion protection. And there will be bimetals. We'll discuss more about that later. And the carbide clad elements, which we'll also discuss more. On the nitrided elements, nitrided elements typically offer the least corrosion and wear resistance. Most steels can be nitrided, but some steels accept the surface treatment better than others. The two most common nitriding processes are ion and plasma nitriding, or plasma nitriding. Plasma and ion, same, they're interchangeable terms. Gas nitriding is the other method. The most common steel grades are nitraloy, and typically nitraloy 135M, 1.8550, and 38 chrome moly and aluminum. The steels containing 1% of aluminum accept the deepest hardening. Correct time and temperature for the particular alloy and desired results are critical to proper nitriding. Nitriding provides an economical option for mild abrasion and corrosion resistance limited to the case depth. Tool steels and some stainless steels can be nitrided to add limited protection. Many tool steels and high-speed steel grades are used in the industry for screw elements as well. They include but aren't limited to D2, M2, 9V, 10V, ASP 60, and there's many more. Most provide better wear resistance than nitrided elements, and most solid tool steels don't offer a great deal of corrosion resistance since they contain little or no chrome, nickel, or molybdenum content. Commonly used stainless steel or high chrome grades include 440C, 420, 1.4122, 10V12, S90V, S10V, X235, and X260. There are more than that, but these are the most common ones. Carbide type and content dictate how effective these steel types are. Many of them provide equal or greater abrasive resistance than the more common tool steels, and all have some degree of corrosion resistance. The austenitic stainless steels and the superalloys and the pH grades. If corrosion resistance is more important than wear resistance, austenitic or non-hardening grades may be the solution you're looking for. In some cases, precipitation hardening grades or one of the superalloys might be a good option. These include the 300 series stainless for austenitic and 17.4 pH for the precipitation hardening, and the Inconels and Hastelloys belong in the superalloy group. Those are also known as high temp alloys. The high chrome and nickel, along with the molybdenum content of these steels, offer excellent corrosion resistance to most corrodants. However, their low hardness typically indicates low wear resistance compared to the materials mentioned in the previous slides. Thermal aging or surface treatment or hard face welding can be applied for improved abrasion resistance, but they still will not compare favorably to the hard face or to the hard tool steels and through hardened stainless steels. The bimetal elements, many of them are tool steels or high chrome steels, can be manufactured as a bimetal consolidation. The core, or the part of the consolidation that makes contact with the shaft, is made from a softer ductile steel, while the outer body or part that contacts your product is made from a hardenable material. This is accomplished by using a powdered metal in a hot isostatic pressing process, or HIP. The result is very wear and corrosion resistant element that contains a ductile inner core. The core can be low carbon alloy steel, which is most common, or an austenitic or pH core. Some of the combinations could be D2 or 10V with a mild steel core, 10V12 or S110V with a mild steel pH, or austenitic stainless steel core. And with the crest welded elements, to increase the wear resistance of some of the low wear resistant austenitic, pH, or superalloys, hard facing can be applied to the crest or the flight tips, if you will. Most materials with low abrasive wear resistance, such as a 300 series stainless, the precipitation hardening grades, Inconels and Hastelloys, can be converted to achieve a moderate degree of wear resistance by crest welding with materials like Colemannoy or Stellite products. The Colemannoys are a nickel-based product containing from 4 to 6% chrome, carbon, 10 to 13% chrome, and they'll result in a hardness of somewhere between 40 and 55, depending on which one we're using. And the common stellite elements are 1, 6, and 12, and they're a cobalt base. They contain from 1.2 to 2.5% carbon and 28 to 30% chrome, and contain tungsten from 4.5 to 12%, and achieve a hardness of 40 to 53 to Rockwell C. Corrosion resistance is generally pretty good since both the element base material and the crest weld material contain high levels of chrome, nickel, and molybdenum. Some hard face materials also contain hard borides or carbides, which provide wear resistance. The cost is higher than tool steel or stainless steel options due to the additional manufacturing and material costs. The hard clad elements, materials like 10V and 10V12, which are already a hardened tool steel or martensitic stainless steel, in the case of 10V12, a brazed tungsten carbide infused fabric can be applied. This provides an extremely hard layer at the crust on an already highly abrasive wear resistant base material. The cladding contains 55% tungsten and 34% nickel and 7% chrome. It's got a resultant hardness of Rockwell C greater than 60 and a metallurgical bond greater than 70,000 psi. The cost is considerably higher, though, due to the difficulty of manufacturing. We'll be discussing the composition of materials now. The tool steels or high chrome steels, the alloy content is critical to its ability to provide abrasive or corrosive wear resistance. Hardness isn't the only measure of the ability to provide wear resistance, though. The balance between the carbon and the carbide forming alloys is key when determining the steel's ability to resist abrasive wear. Some of the common alloying elements are iron, carbon, chrome, nickel, molybdenum, manganese, vanadium, tungsten, cobalt, and niobium. Carbides are the primary component for a steel's ability to provide wear resistance. The hard carbides held in the steel's matrix provide a bearing surface against wear. And the harder the carbide, the greater the wear resistance. Carbides are formed when the alloys such as chrome, tungsten, molybdenum, or vanadium pair with the carbon during the transformation between the liquidus stage and solid during the steel manufacturing process. Heat treatment can also help form and stabilize carbides. Not all alloys are created equal when it comes to forming carbides. Vanadium and niobium, for instance, are stronger and more stable carbide formers than iron and chromium. They'll absorb the carbon first and remain stable through heat treat. Chromium and iron will absorb the remaining carbon, but will also precipitate carbon out during the heat treat process. The strength of these alloy elements are ranked from the lowest to the highest, with iron being the lowest and niobium and vanadium being the highest. The higher ranking alloys also produce harder and more resistant to wear carbides. Comparing the hardness in carbides, looking at D2 and 10V, both hardened to Rockwell C58. D2 contains 1.5% carbon, 11.5% chrome, and less than 1% molybdenum and vanadium. 10V contains 2.24% chrome, or carbon, 10% vanadium, 5% chrome, and 1% moly. Both have the same hardness, but 10V with its higher carbides will have 2 to 3 times better wear resistance. In the high chrome alloys, the chemistry of the two elements reviewed below both contain 2.3% carbon. However, alloy A contains 10% vanadium and uses all 2.3% of the carbon to form hard vanadium carbides, leaving all 12% of the chrome within the matrix. Alloy B contains less vanadium and other high-ranking alloys, which allows the chrome to also pair with carbon for carbide formation. The result is a lower wear-resistant carbides and less chrome remaining within the matrix for the corrosion resistance. Further examples on the next 2 slides. In this slide, You can see that alloy A has 2.3% total carbon, so does alloy B. Carbon is vanadium, niobium, and moly carbides are 2.3 and 1.2 respectively. The available carbon for A and B, alloy A is 0, alloy B is 1.1, and so on down the line. Although alloy B has 20% more chrome, 13.5% of it is transformed into carbides. So therefore you'll have a lot less corrosion resistance. Comparing wear rates between alloys A and B, the harder carbides of alloy A translate into a harder, increased abrasive wear resistance. The higher levels of matrix chrome also provides increased corrosion resistance. Corrosion resistance comes primarily from the alloy content of the material. Steels that contain high chrome, nickel, and molybdenum will have an increased corrosion resistance. For austenitic steel such as a 316 stainless steel, the full amount of these alloys within the matrix provides corrosion resistance. For martensitic stainless, it's important that these alloys are balanced properly with the amount of carbon in the chemistry. Example being that the higher the percentage of chrome remaining in the matrix provides more passivation, which protects the iron base from corrosion. We see it once in a while where some processes will remove the passivation layer from the surface of the material, allowing a short time of corrosion in the base material until it repassivates. So, and then it just keeps going like this. So it's important to have the whole thing balanced. Some anti-abrasion methods can also provide limited corrosion resistance. Nitriding does provide a small amount of corrosion protection to an otherwise non-corrosive resistant materials due to the nitrogen layer. Cryogenic treatment can provide a slight increase in corrosion protection to an already corrosion resistant material. Sorry about that. Methods of material manufacturing. For conventional cast, HIP, as we talked about before, we're doing a powdered metal and a hot isostatic pressing. Bimetal, hard facing. Hardening and surface treatments. The conventional cast method, solid through hardened or surface treated screw elements are manufactured from wrought steel. This slide shows the process from the melting to ingot casting to the bar rolling to the finished wrought bar. D2, M2, 440C, 1.4122. Those steels are all through hardened wrought steels. There's quite a few more. 316, 17, 4pH and the super alloys are wrought, whether they're annealed, aged, or surface treated. They're all done in the same method. Nitraloy, the 1.8550, as well as the other nitriding grades, they're all wrought steels. The atomized powder process is that's a powdered metal. The powdered metal grade steels are produced through an atomization process. A simple explanation of atomization is the melting of a given mix of raw materials, forcing it through a nozzle where the high velocity inert gas impinges the metal stream, atomizing it into tiny spherical particles. The particles rapidly solidify as they fall through a cooling tower and into a cryogenic quench. The result is high purity pre-alloyed metal powder that Powdered metals are really homogeneous. I mean, the same alloy, there's no distribution problems with the alloys with the powdered metal. They're generally melted together, all the alloys together, so that you get a real homogeneous product. The hip materials, continuing, the powders are then screened to segregate particle size for proper tap density properties. The screen powder can be blended with other atomized alloys or elements to a given recipe, but generally, most of our materials, or maybe all of them, are pre-alloyed, so they're alloyed before they get atomized. It gives us a more homogeneous product. We don't get any settling of heavier particles towards the bottom of the hip containers. Hot isostatic pressing is a simultaneous application of heat and high pressure. The typical hip units comprise of a furnace with an extreme strength pressure vessel. Using a specific cycle, the temperature will be ramped up to just below the melting temperature of the selected powdered metal alloy. Argon gas will fill the vessel, exerting a force equally on all surfaces of the workpiece. The workpiece will have to be held under heat and pressure for a given time frame per cycle requirements. With most of our powders, or probably about 75–80% of them, that the hip containers are put into one of these vessels. The thing is sealed off. They ramp the temperature up to, or they ramp the pressure up, I'm sorry, up to about 5,000 psi. Then they ramp the temperature up to close to 2,000 degrees. It's below the melting point. It's still a powder at that point, but then they ramp the pressure up to about 15,000 psi, and it's held there for a certain length of time, and then slow cooled and removed from the vessel. And what it does is form a metallurgical bond. Ours are in the bimetal. Well, we'll read about the bimetal shortly. But it forms a solid then at that point. All powdered metal steels must be processed through a hip cycle in order to be utilized for solid or bimetal screw element material or any other solid or bimetal application. The exceptions would be for powders that are used in PTA or high velocity welding or additive manufacturing and 3D printing. For hip, the containers are filled with powder, degassed and sealed prior to consolidation. And bimetal materials, the bimetal screw elements utilize both PM grade material and the hip process to form a consolidation of both hard wear and corrosion resistant material and the ductile non-hardenable metals. From a consolidated bar, a finished element can be manufactured. And in the slide, if you take a look, the slide in the lower left shows the consolidation as we receive it from hip. It's got a container on the outside that contains the powder, and next, just to the right of that, you can see, if you look closely, you can see the bond line, or the difference between the two metals, the core and the outer material. And the slide, or the picture on the right, shows a finished element with the soft core. You should be able to see the line separating the two. We've done some tensile testing on that, on our metallurgical consolidations, where we actually pulled, made the tensile test bars according to the standards, pulled them apart, and the 1018 or the soft core will actually break before the bond breaks. We've never had any separate. The hip alloys allow the use of many different alloys for wear and corrosion resistance. Powdered metal alloys provide better material properties than standard tool steels due to the purity in the atomization process. Powders can be blended with other alloys to tailor a material for a specific need. Many wear-resistant powders are readily available for HIP, ranging from conventional tool steels like D2 to the higher alloyed materials like 10V and 15V. For corrosion and wear resistant, many high chrome alloys are available, such as 10V12, S90V, S110V, X235, X260, S115V, and S125V are other products. There's many on the market already that can be used. And the super alloys like the nickel-based colmanoid products or cobalt-based products can also be used in a HIP process. Many of these powder options are also available for use with stainless steel or other corrosion-resistant substrate core materials. Hard-faced elements using the PTA or the TIG welding or other welding methods powder metal or cast rod wire can be used to be applied to the flight crest or other areas of the screw element. Common hard face materials like colmanoid and stellite grades. Using the top two photos are showing the plasma thermal arc on a single extruder screw, and the bottom photos are representative of a TIG welded screw element. We typically groove those prior to forming the screw element or machining the screw element out of it. So that's why it just looks like a cylinder with some weld around it. But they're grooved, and we fill the groove with the hard face material. Hardening methods: quench and temper is a hardening process used on high carbon and high alloyed steel. Common methods are salt bath, atmosphere, and vacuum. Typically, we employ the salt bath or the vacuum, depending on which material we're heat treating. Material examples are D2, 10V, 440C, S90V, most of our through hardening steels. The advantage is they provide a uniform hardness throughout the material thickness. The disadvantage is through hardened materials can be brittle and prone to chipping and cracking. Age or precipitation hardening is a method used to strengthen and harden low carbon, highly alloyed steels. Examples are the 17,4-pH Inconels and Hastelloys, often referred to as super alloys. The advantage is they provide strength and limited abrasion resistance to high corrosion resistant materials. They can increase the abrasion resistance with hard facing. The materials this process applies to are still considered to have low abrasive wear properties. And surface treatments include nitriding, a nitrogen surface hardening process that can be used on low or high carbon steels. Common methods are ion or plasma nitriding or gas nitriding. Material examples are nitroloy, the 1.855, etc. Advantage: it provides a very hard layer that provides good abrasion resistance. The disadvantage is that the layer is very thin. That number on there is incorrect. I'll fix that. It should be between 0.1 and 0.5 millimeter thickness max, and the hardness decreases with the depth. This process uses extreme low temperature, or cryogenic treatment uses an extreme low temperature, minus 190 C, as a method of additional tempering and stress relieving high alloyed materials. It also can be used, cryogenic treatment can also be used in the through hardened steels to, it is an additional tempering by converting the retained austenite to tempered martensite. Material examples are 10V, D2, S90V, and our 10V12. It can slightly improve wear resistance while converting retained austenite, as I said. It can also slightly increase corrosion resistance by refining the grain structure and reducing intergranular corrosion. The disadvantage is the increased wear and corrosion resistance is incremental and not equal to a change in the alloy and or material type. It does add cost too, so the additional wear and corrosion resistance is minimal, usually not worth the extra cost. Talk about the material testing methods. For abrasion testing, corrosion testing, wear and corrosion ratings. The ASTM G65 is widely recognized and is approved test method for measuring abrasive wear resistance. It's more of a comparative wear resistant test to to compare using a dry sand actually. The test measures volume loss in cubic millimeters after a sample has been exposed to dry sand erosion using a tightly controlled process. There is a diagram of the test equipment, and dry sand is fed into a rubber wheel as the test sample is forced against a wheel. A before and after photo of the sample is shown in the below right. For corrosion testing, ASTM G31 is a widely recognized method used to determine the corrosion resistance between various metals and specific corrodants. It requires a small sample similar to the abrasion testing, but utilizes submersion into a boiling acid solution rather than mechanical action. It measures the same way as volume loss and surface condition of the sample are measured and compared to other test specimens. Other test methods also used are ASTM G48, pitting and crevice corrosion resistance, ASTM A262 is standard practices for detecting susceptibility to intergranular attack in austenitic stainless steels, and ASTM B117 salt spray. Typically, we use ASTM G48 and or ASTM G31. We have used the A262 for testing intergranular attack in austenitic stainless steels, but we have already performed those tests, so we have the results. Here's an abrasion and corrosion resistance chart. This is only to be used as a guide, as a comparative guide to other steels rated on there. Shows the abrasion resistance in blue and the corrosion resistance in red. So as you can see, the tungsten carbide clad at 65 Rockwell is very abrasion resistant, moderately corrosion resistant. 10V tool steel is the same. The wear resistance is much higher than the corrosion resistance. Till you get down to the 17.4 and the 300 series stainlesses, the duplexes, and on down the chart, then you see the corrosion resistance creeping up and the wear resistance creeping down. Century offers all the materials mentioned in this webinar, plus many more. As I said at the beginning, we offer more than 80 material options for barrels, screws, and shafts. And we're continuously researching and testing materials and material combinations to address specific needs of our customers. Contact your Century representative to get more information. They will contact the necessary people, whether it's me or our metallurgist, the metallurgist that we contract with. We will get the information to you. And have you considered on-site training? We can conduct the training at your facility, schedule at your convenience, and it's customized for your machines and products. So contact us again for your request a quotation. Please keep in mind that there's many factors that need to be taken into account in order to select the correct metallurgy for your particular product process. We need to know the product rheology, the temperature, any additives, the RPM, the material and fill rate, your production rate. There's a lot of questions that need to be answered. Whether there's phosphoric acid, sulfuric acid, hydraulic, whatever your corrodant might be, we need to know that, as well as any fill that you might be doing, whether it's glass or calcium carbonate, whatever. But all of those and more need to be answered before we can properly assess your need. So please contact your representative to get those questions answered as well. They'll direct them to the right people. And that pretty much concludes the seminar. So thanks for participating. And send your screw material questions and suggestions for future webinars. And mark your calendar for the November 8th webinar, Understanding Extruder Barrel Metallurgy.
Okay, so we do have a few questions, so.
Okay.
So we'll start with, let me see. Go up here. Got a screen for them. Okay, so one person wants to know what are the benefits of having a soft core, and is a soft core an element always recommended when using hardened elements?
Yes, the soft core is recommended only for the hardened elements, and one of the advantages or one of the benefits of having a soft core is that it conforms to any irregularities in the shaft more readily and gives you a better torque transfer. It also takes up some space so that you're not putting high dollar product down where it's not needed and there's no benefit to it.
Okay, so so they also want to know where the elements are manufactured.
Elements are manufactured here in Traverse City, and depending on which product line it is, they could be manufactured at our plant in Germany, Extracom, or at our plant in Nanjing, China. That would be RIA. But most of them are manufactured right here in Traverse City.
Okay, so the next question are higher ranking alloy elements also, do they also get more brittle?
It really depends on the alloy and the heat treatment, but typically, you know, if it's a higher alloy, it's higher alloyed for a particular reason. It generally increases the hardness, which usually translates into more brittle.
Okay.
But the profile shape of the element doesn't usually lend itself to a need to be real ductile, you know, and maybe in narrow paddle kneading blocks it might have an effect, but for the most part in our hardness ranges the materials aren't overly brittle.
Okay, so what are the cost differences between standard elements, hipped and hard face material? And an estimated guess is okay.
I'd have to guess they're probably around 25% higher.
Okay.
But that's just a guess. I don't do the cost estimating myself, so I can't say for sure, but I would guess it's around 25%.
Let's see. Okay, so what is the maximum recommended temperature for cleaning screw elements? Some companies use pyrolysis furnace use a pyrolysis furnace for cleaning.
Pyrolysis is an excellent method for cleaning them, for getting rid of the other material. Most of our materials, we recommend 800 degrees F as a max. Because then that's pretty much safe with any of our screw elements. There are a few that you could go a little bit higher than that, but typically 800 degrees F will do the job.
Okay, so our next question is, with increasing chromium with increasing the percentage of chromium, the wear resistance decreases. If this is correct, then for higher wear resistance, what is correct, 10V or 10V12?
Because we have a good balance in our chemistry for the 10V12, 10V12 is a good balance. All of the carbon is used up with the vanadium, and the chrome is left in the matrix. So we end up with a good wear and corrosion resistance from that particular alloy mix.
Okay, so can you summarize the difference between 440C and 1.4122?
Yeah, 440C, the 1.4122 is similar to 440A. That would be the closest US grade or AISI grade. It would be 440A. I can't remember the chemistry of either of them right offhand. The 440C does have a little more hardenability. 440A is typically just a few points softer in Rockwell C scale.
Okay. It looks like that is all the questions that we can probably answer here. We'll probably have to answer the rest by email.
Okay.
Because they're just a little bit more complicated.
Okay.
So it looks like that ends the webinar for today. So you can contact your representative. It's shown on the screen, and you can contact them with any further questions. And so we'd like to thank you all for attending, and we'll answer all your remaining questions by email. So have a great day. Thank you.